Hi everyone, today I'll be going over problem number 990, satisfiability of equality equations. So this problem at a high level is asking if we can or cannot solve a system of equations. That is there a solution? So if to help you out, to help you guys out here, if we take us back to middle school or a high school algebra, we're given a set of equations like a equal to b equal to c, or a not equal to d equal to b equal to a, and we need to ask ourselves, hey, can we, like, is this set of equations like satisfiable or not? So in the first example, right, we're given two equations, a equal to b not equal to a, and we say that this is not satisfiable because if we assign the values of 1 and 1 to a and b, we satisfy the first equality but not the second, which is an inequality. And if we assign two different values, a equal to 1, b equal to 2, we satisfy the inequality but not the equality. In the second example, b equal to a equal to b, if no matter what value we assign to a and b, as long as both of them had the same value, 1, 2, or -1, we satisfy both equations. So to come back to the word problem description, we're given an array of equations that represent relationships between variables in the form of strings, where each equation is of length 4 taking on two forms, x equal to y or x not equal to y, where x and y are lowercase letters, not exactly different, representing one letter variable names. We need to return true if it's possible to assign integers to variable names satisfying all the equations, or false otherwise. All right, so let's take a look as to why this is one of my favorite problems. Why do I love this problem? A couple of different reasons. The first being the real-world applicability. So it emulates the modeling and the solvability of equations done in contexts like Wolfram Alpha, Mathematica, and a TI-83 graphing calculator. The second being the test of reading comprehension skills. So we stress test the developer on working through complex case studies. The third reason being the testing of multiple data structures. The satisfiability problem can involve a combination such as graphs, hash maps, recursion, and union find, commonly found in interview settings. And the last being a test of recursion. We test skills like DFS, BFS, or graph exploration type of recursions, either using a queue, a stack, or nested or function calls. All right, so let's take a look at the constraints of the problem. So let's come down over here. We have a couple different constraints where we're given the following. There's only 500 equations max, and the equation's input is always in a reasonable form. So the length of every equation is 4 characters, where the first character, the last character are single letter variable names in the English language, and the second two characters are either an equality, double equality, or an inequality. All right, so at a high level, like, what's kind of the approach that we sort of take to the problem? There's a couple different approaches, but personally, I think the easiest is actually to think about this problem kind of more like a graph. So let's go to the first figure that I have diagrammed here, right? If I split the problem of the equations into those where there is an equality and those where there is an inequality, it's kind of easy for us to model the problem as a graph. So in the first case, we go through each equation that's an equality, and we ask ourselves, okay, for every variable that is equal to another variable, there should be an edge between those two variables. So in this example, with connected component 1, where we have a equal to b equal to c, and c equal to e, we have a graph that resembles a syncly linked list. A connected to b connected to c connected to e. And then if we can extend these equations to equalities to other equalities, like connected component 2, where we have g equal to h and h equal to I. So we create a second connected component because none of the variables g to I are related to the variables from a to c and e. It's its own standalone graph, and we can also create one for k if it's a variable that existed but wasn't part of an equation. As you can see here, because we're focused on what's equal first, we can assign globally unique values like 1 or 2, 1 for a to e, and 2 for g, h, and I, and we can see that this is satisfied because it's clear that from a to b to c to e, the values are all 1. From g to h to I, the values are all 2. But then we come to the inequalities, like e not equal to g, k not equal to a, and a not equal to c. And we have to start to ask ourselves questions, does the inequality hold true or not? So in the first example, e not equal to g, this is going to be true because e is set to 1, g is equal to 2. In the second case, k not equal to a, that's also true because these are two different connected components. There's no way to traverse from one node to another node and vice versa. But in the last case, a not equal to c, this evaluates to false because a and c are equal to 1. There exists a path between node a and node c in both directions. Therefore, it cannot be an inequality because there's a path that exists, and the path that exists corresponds to an equality. All right. So now that we have kind of the understanding at a diagrammatic approach for how to tackle the problem, let's take a look at a code-based approach.